Every day, professionals in heavy industries operate in environments where the margins for error are razor thin. Whether extracting resources offshore, or mining deep underground, or building vertical infrastructure, the inherent risks of the job remain a constant reality. Over the last few decades, corporations poured billions into safety programs, compliance training, and behavior management. By standard metrics, it worked. Recordable injury rates, the minor cuts, sprains, and trips, fell by approximately 70% from the early 1990s to 2020. This chart compares that celebrated drop against a much starker metric. The steep downward curve represents the total recordable incident rate. The rigid flat line beneath it represents the U.S. Bureau of Labor Statistics workplace fatality rate. While minor injuries plummeted, the rate at which workers are killed on the job barely moved. In 2024 alone, the BLS recorded 5,070 fatal work injuries. Despite decades of modern safety management systems, that number remains stubbornly high. This divergence creates a false sense of security. Executive teams and safety managers look at a low recordable injury rate and conclude their critical risks are effectively controlled. They equate a lack of minor accidents with a lack of fatal exposure. Relying on these lagging indicators blinds an organization to its actual vulnerabilities. Tracking how many people tripped yesterday offers zero predictive value for who might be caught in a high-pressure valve tomorrow. For nearly a century, safety programs have been built on a single historical model, the Heinrich or Bird safety pyramid. This diagram posits a fixed ratio, 300 near misses to 29 minor injuries to 1 fatality. The operating logic is simple. If you reduce the volume of minor incidents and unsafe acts at the bottom of the pyramid, the major injuries and fatalities at the top should proportionally decrease. But the empirical data proves this logic false. Recordable rates dropped drastically while fatality rates stagnated. The bottom of the pyramid shrank, but the top stayed exactly the same size. By treating all incidents as equivalent points on a single continuum, organizations spread their finite safety resources across hundreds of low-consequence events. A paper cut gets the same investigative weight as a dropped suspended load. Chasing the bottom of the pyramid has reached diminishing returns. To actually prevent catastrophic events, the industry requires a different method of measuring and predicting risk. Minor injuries and fatalities do not share the same DNA. They operate through distinct causal pathways. In the first pathway, a worker makes a routine error around a low-energy hazard. They trip over a cord or slip on a wet floor. The result is a twisted ankle or a bruised knee. This diagram illustrates the divergence. The second pathway involves high energy and a critical control failure. When a worker interacts with immense physical forces and the system's defenses fail, the result is a serious injury or fatality, a SIF. These high-energy hazards include gravity, massive mechanical motion, pressurized chemicals, and high-voltage electricity. They are the unforgiving forces native to industrial work. Research indicates that breakdowns in the critical controls isolating these specific energies explain almost all SIFs, but they factor into nearly zero non-SIFs. Equating a minor slip with a near miss involving heavy machinery obscures the actual lethal threats embedded in the operation. The focus must shift entirely to managing high-consequence energy. Leading organizations have stopped counting total incidents and instead process their data through a specific classification system, SIF potential, or PSIF. This requires decoupling what actually happened from what could have happened. You evaluate the exposure, not the resulting injury. This tree filters data through 3 strict gates. Gate 1 asks, was there high energy exposure? Gate 2, was a critical control ineffective? Gate 3, could the outcome have been fatal? If it passes all 3, it's classified as a PSIF. Applying this filter strips away the noise. It ensures that investigative resources, governance, and leadership attention are directed exclusively towards scenarios with the capacity to kill or maim. A near miss without an injury is no longer dismissed. It becomes a leading indicator of control health, providing the precise, structured data required to predict future system failures. The PSIF framework provides the right metrics, but modern industrial operations generate overwhelming volumes of it, from permit records and sensor streams to daily observation logs. manual human review cannot reliably detect subtle, multivariable patterns hidden within millions of data points. A severe incident rarely stems from a single failure. It involves specific high-energy tasks, colliding with severe weather conditions, tight scheduling pressures, and complex contractor handoffs. Predictive algorithms map this operational complexity. They cross-reference thousands of variables to identify recurring precursor combinations that humans simply cannot see. Machine learning models trained on historical SIF data process real-time inputs to forecast elevated risk states, allowing managers to intervene before the work even begins. Simultaneously, natural language processing algorithms scan decades of unstructured written incident reports, instantly extracting hidden behavioral and equipment trends that would take teams of analysts years to categorize. On the ground, computer vision tools continuously monitor critical control compliance, identifying unsecured loads or missing spatial barriers at a scale impossible for human supervisors. These analytical capabilities close the gap between data collection and action, bridging the organization from reactive outcome management to proactive risk intelligence. Data models and algorithms are only part of the equation. To actually reduce risk, this predictive intelligence must be integrated with human and organizational performance, or HOP, principles. Historically, many behavior-based safety programs stalled because they narrowly focused on policing worker actions, inadvertently reinforcing a culture of blame that drove reporting underground. Analytics redirect that focus from the worker to the environment. They reveal where the system design creates error-likely conditions. The data shows exactly how extreme production pressure, fragmented training, or flawed equipment interfaces systematically undermine critical controls on the front lines. Predictive insights fail if they are wielded for punishment. Their purpose is to facilitate blame-free learning reviews and drive the physical redesign of resilient operational systems. This integrated architecture consists of 4 layers: foundational data, analytics intelligence, human performance, and governance. The foundational SIF classification feeds directly into the predictive models above. These insights are then handed to the top tiers, fueling HOP learning reviews and providing metrics for executive oversight. This architecture requires replacing the total recordable incident rate with metrics like critical control verification rates, the percentage of high-energy work with verified defenses, and the precision of the predictive models themselves. The results are measurable. Construction firms utilizing AI predictive tools have accurately forecasted 75% of recordable incidents on high-risk projects, and major mining operations have dropped injury frequencies by 75% over 6 years. Executing this framework is a strategic leadership responsibility. It requires executives to transition from rear-view scorecard management to credible, field-visible risk governance. Decades of tracking minor injuries failed to stop the most catastrophic events. Moving beyond the traditional pyramid paradigm to a data-driven, systems-oriented approach is an ethical and operational imperative for modern high-hazard industries.